This is 24th lecture, and we are going to discuss the hybrid and transmission parameters of two ports. We have already discussed the open circuit Z parameters and the short circuit Y parameters. The hybrid parameters or the H parameters are defined like this. Our convention for the two port is the same. V1 I1, V2 I2, conventions are the same, and the quantities that we take as dependent variables are one voltage and one current, V1 and I2, and this should tell you why the parameters are called hybrid. They are not both voltages, they are not both currents, they are one voltage and one current. Not only that, the voltage and current are not at the same port, they are at different ports. So, there is a hybridization of all kinds, and the the quantities are written as H11 I1, the independent parameters are I1 and V2. So, H12 V2, H21 I1 plus H22 V2, these are the four parameters. And if you look at the definition, which I shall repeat in the next slide, V1 equal to H11 I1 plus H12 V2, I2 equal to H21 I1 plus H22 V2. The thing to remember is it is the input voltage or voltage at port 1 and current at port 2. Okay. Now, if you look at the definition, H11 obviously is V1 by I1 with V2 equal to 0, the output short circuited. Let us look at, we will go very slowly. Let us look at the condition. V2 equal to 0 means this is short circuited. This is the current I2, which is not of interest. What is of interest is V1 by I1, and therefore it is the input V1 by I1 is the input impedance under short circuited output. So, what is the admittance? By definition, this admittance is Y11, and therefore, H11 is simply related to the Y parameter Y11. It is input impedance under the output short circuited. Output short circuited gives the input admittance as Y11, and therefore, H11 is Y11, and this is a short circuit driving point impedance. Short circuit driving point impedance. Let us look at H12. By definition, H12 is V1 by V2 under the condition I1 equal to 0. But before we take this, let us take the other one. H21 is equal to I2 by I1 under the condition V2 equal to 0. All right. So, H21 can be calculated from this diagram. All right. Under the condition V2 equal to 0, find the ratio of I2 to I1, and that shall be H21. And as you see, H21 is a current transfer function. Agreed? It is a dimensionless quantity, current transfer function, that is the output current divided by input current with the output short circuited. So, this is a short circuit SC, short circuit current transfer function. All right. Now, let us look at the other two parameters, namely H12 is equal to V1 by V2 I1 equal to 0, and H22, if you see, it is I2 by V2 with I1 equal to 0. All right. And I1 equal to 0 means open circuit at port number 1. So, let us draw the circuit, let us draw the block. Port number 1 is open circuit, and therefore, no current, the only thing you can measure is the voltage, and port 2 there is a voltage excitation V2. Obviously, the excitation cannot be at port 1. Why not? It is open, and therefore, any source that you connect will drive a current, and therefore, the source must be V2, I1 equal to 0, and all that you calculate now is V1 by V2. V1 by V2 is the actual transfer function. So, this is the reciprocal, no, I beg your pardon, this is an open circuit, not V2 by V1. You see, V2 is the excitation and V1 is the response. So, it is correctly V1 by V2. This is therefore the reverse voltage transfer function, but also open circuit reverse voltage transfer function. Reverse because it goes from port 2 to port 1. Our convention is that power or energy travels from port 1 to port 2. This is another way of obtaining a transfer function. This is an open circuit reverse voltage transfer function. And if you look at H22, H22 is I2 by V2 with I1 equal to 0, and therefore, I2 by V2, H22 therefore is an open circuit driving point, I2 by V2 is admittance, and therefore, this would be simply equal to 1 over Z22. Agreed? So, H22 is driving point, open circuit driving point impedance function, no, admittance function. Now, let us look at the dimensions. H11 was impedance and its driving point, and it is short circuit. H11 is short circuit driving point impedance. H22 is open circuit driving point admittance. H12 is open circuit reverse voltage transfer function, and H21 is short circuit. Is it a forward or reverse? Forward current transfer function. Now, you see the hybridization. It is a mixture of all kinds of things: impedances, admittance, current transfer function, voltage transfer function, under open circuit or short circuit, reverse or forward, and that is why these parameters are called hybrid parameters, and they have a very important application in dealing with transistor circuits. As you know, the hybrid pi equivalent circuit is the most universal and the most desirable kind of equivalent circuit for a transistor, and they originate from the H parameter model of a general 2 port. Let us take an example. Suppose we take the familiar pi network YA, YC, YB. This is port 1 and port 2. The first thing we do is H11. As you know, H11 is 1 by Y11. H11 is the impedance, okay, 1 by impedance looking here with this short circuited. So, it is simply the parallel combination of YA and YC. So, 1 over YA plus YC. It is an impedance. It is the input impedance with the output short circuited. In a similar manner, H22 would be the impedance measured from here with port 1 opened, and therefore, it would be 1 over, is that right? 1 over Z22, agreed? 1 over Z22. Now, obviously, H22 is an admittance, isn't that right? So, the admittance measured here would be YB plus the admittance of the series combination of these two, which is exactly equal to YA YC divided by YA plus YC.
Should H11 be YA, I mean 1 by YA in parallel with 1 by YA plus 1 by YC?
No, H11 is an impedance
Yes, sir.
consisting of YA and YC in parallel. So the total admittance is YA plus YC, and therefore the impedance is 1 by YA plus YC. Okay, is this result correct? Let us find out the other two parameters, that is H12 and H21. H12, for example, for finding H12, what we have to do is YA, let me draw the network first, YC and YB. H12 by definition is V1 by V2 with I1 equal to 0. It is open circuit reverse voltage transfer function. Now this comes in parallel with V2, so it has no effect. So V2 therefore divides, there is a potential division between YC and YA. Therefore V1 would be equal to V2 1 by YA divided by 1 by YA plus 1 by YC. Is that clear? This impedance, that is ZA divided by ZA plus ZC, not YA divided by YA plus YC. This is in fact this is V2 YC divided by YC plus YA, and therefore H12 is V1 by V2, therefore it is simply Y sub C divided by Y sub C plus Y sub A. Is that clear? This is H12. Now to find out H21, H21 is by definition I2 by I1 with V2 equal to 0. Is that correct? V2 equal to 0. So let us see, we have YA, we have YC and we have YB. Obviously the excitation is I1, there is a current source I1, this is 0, and you are required to find out this current Y2, which is obviously the current in Y sub C also, because this goes out of picture being short circuited, and therefore I2 would be equal to I1 minus I1, then YC divided by YC plus YA. Is that okay? And therefore H21 would be equal to minus YC divided by YC plus YA. And if you recall what is H12, you see that this is exactly minus H12. And why and what does this indicate? This indicates the condition for reciprocity. We assume that YA, YB, YC are bilateral elements, that they pass current equally well in both directions, and therefore what was Z12 equal to Z21 or Y12 equal to Y21 in terms of Z and Y parameters now transfers into H21 equal to minus H12. This negative sign should be noticed. This is these three are identical conditions, that is, this condition is equivalent to this condition and the whole thing is equivalent to the third condition. These are all conditions for reciprocity condition, reciprocity. Let us take another example.
The latest sign current, because it's a reverse, one is a forward parameter transfer function.
No, it is not because of that. It is because of the directions of I1 and I2.
Sure.
Both go in. So if there is a current I1, if there is a current I1 feeding here, the current through IC must flow in this direction, whereas our convention is that I2 goes in. That is why this sign is negative.
This negative sign doesn't imply anything, but for this current direction.
With this convention, H21 must be equal to minus H12. Okay?
So for a network you find H21 is equal to minus H12, then we can say that it
It is reciprocal. It is a necessary as well as sufficient condition. Yes, that is correct. In fact, this is a test for reciprocity. Okay. Let us take another example. And this example is that of a two-port having the particular property that whatever you connect at port number 2, a load ZL reflects at the input as the negative of ZL, that is Z in equal to minus ZL, all right, which means that you have if you connect a positive resistance here, it will reflect as a negative resistance, and this is the way to make negative elements. We have always talked of positive R, L and C. There is a way of making negative elements, and this is a two-port which is not a dream two-port. It can be realized in practice, and such a two-port goes by the name of negative impedance converter, NIC. Obviously, it converts a positive impedance into a negative impedance, and this is why it is called a negative impedance converter, or NIC. The NIC has the property that the impedance at the input is the negative of the impedance of the terminating impedance. Okay. Let us write it again, Z in equal to minus ZL. Now, if I indicate the voltages and currents, this is V1 I1 and V2 I2. You notice that Z in is V1 by I1 minus ZL is V2 by I2? No. The relation between V2 and I2 is V2 is equal to minus I2 ZL, isn't that right? Because the directions do not agree, and therefore this sign would be plus. Is that okay? Z in equal to minus ZL indicates that V1 by I1 is equal to V2 by I2. Obviously, this relation can be satisfied in many ways, and the way that usually it is tried to be satisfied in an NIC is that V1 is the proportional to V2, and so I1 is proportional to I2. If V1 is K times V2 and K is a constant, then I1 must be equal to KI2. Okay. If I write these relationships in the form of H parameters, that is, my NIC is characterized by V1 equal to K V2, I1 equal to KI2, and my H parameter relationship is between V1 and I2 as dependent variables and I1 and V2 as independent. So, H11 I1 plus H12 V2, I2 is H21 I1 plus H22 V2. If I compare this relation with this relation, then obviously what I get is H11 is 0, V1 equal to simply K V2, and H12 is equal to K. Agreed? Is it okay? All right. And I compare this relation with this, but before that let me convert this as I2 is equal to 1 over K I1. I can write it that way. Now I compare this with this, then I get H21 as 1 over K and H22 is equal to 0. Therefore,
The assumption that V1 is equal to KV2 and I1 is equal to KI2. So we have taken it.
Pardon me?
So we assumed it something.
No, I made a statement there that this is the usual way one tries to satisfy the NIC condition. The practical circuits are built on this assumption. You can have other kinds of assumption also, that V1 equal to KI1 and V2 equal to KI2. Yes, you can do that. Okay, there are many other ways.
So here you are trying to synthesize the circuit, the NIC.
No,
So
I am trying to show you an example of a two-port which is neither reciprocal nor passive, okay, and it is a circuit which can be made with transistors or op amps. Alright, I am not synthesizing what is inside NIC. Inside NIC you will look at in a different course. What I am showing is that the NIC is an example of a 2-port which is neither reciprocal nor passive. It is not reciprocal is obvious because H12 is not equal to H21. Is it passive? Well, for that you see V1 I1, the total power that goes into the network, V1 I1 plus V2 I2, this is the total power that goes into the network, and this is equal to, you see, V1 equal to K V2 and I1 equal to K I2, and therefore I can write this as V2 I2 1 plus K squared. Agreed? V2 I2 1 plus K squared. Also V2, no, V1 I1 is K V2 multiplied by K I2. So K, I don't understand why it should be 1 minus K. I am substituting for V1, I am substituting for I1. K V2 multiplied by K I2 is K squared V2 I2. I am writing this product in terms of V2 I2. I have a purpose. You see, V2 is equal to minus I2 ZL, and therefore this is equal to minus I2 squared ZL 1 plus K squared. Alright. Therefore, the power that goes in can be negative, this sign negative. I2 squared, if it is a resistive network, let us say, if ZL equal to a positive resistance RL, then I2 squared is a positive quantity, and therefore the power that goes in can be negative, which means that the 2-port generates power. It does not absorb power, it generates power. The condition for passivity is that V1 I1 plus V2 I2 must be greater than or equal to 0. It must either absorb power or may not absorb power, but it should not generate. If it is greater than 0, then the network we say is lossy, that is, it dissipates power, it absorbs power. If it is equal to 0, then we say the network is lossless. On the other hand, what we have here is negative, and therefore the network generates power, which means that the network is active and non-reciprocal. And obviously, if it is non-reciprocal, it cannot be made out of RLC elements, positive R, positive L, positive C. We must have non-reciprocal elements, non-unilateral elements like diodes or transistors, or a combination of transistors to make an op amp. In fact, an NIC can be made with transistors and or op amps, and simple circuits can be built to demonstrate the action of NIC. If you are interested, we shall look at some circuits at a later stage. Our next concern is the ABCD parameters. ABCD parameters, and we shall have very interesting examples of ABCD parameters also. ABCD parameters, as you know, are also known as transmission parameters, and why they are so denoted, why they are called transmission parameters shall be obvious. They are also sometimes called T parameters, capital T. We do not use a small t because small t we reserve for time. Capital T, yes, you can use, but the in the literature right from the days of Lord Kelvin. Lord Kelvin was the originator of the transmission line concept, transmission line theory, and he used ABCD parameters, and therefore we have respects for the older generation, and we still call them ABCD, although it is a bit messy, 4 things to be mentioned. But capital T, you see, has many other connotations. It is also used for time, temperature and what not. So, we refrain from using all this, we will call them ABCD parameters. And the relationship now is based on the input parameters being looked at as dependent parameters, V1 I1 and V2 I2 as the independent parameters. That is, in terms of matrix notation, I will come to the actual notations later, actual equations later, but in terms of matrix notation, there is a 2 by 2 matrix which relates to V2 and I2, and one thing that must be remembered is Lord Kelvin used a negative sign here, V2 minus I2.
So you told us earlier that V1 and I1 are used as independent parameters.
No, they are dependent.
Transmission.
They are dependent. Did I say they are the independent? Well, then I made a mistake. One of the n mistakes that SCDR does in the class, okay, where n may be a large quantity, but it is your responsibility to correct them. What I want you to notice is this negative sign. Well, if I look at the 2 port, you say V1 I1, V2 and I2, what it means is that I2, the output current is taken as going out of the network instead of coming in. If it was coming in, we should have used a plus I2, okay. And Lord Kelvin argued that whatever I feed in, if I feed in a current in this direction, well, I will take it. Lord Kelvin's convention was that I will take it going out, okay, the current going out. So, this is why, to keep track with modern practices in which a 2 port parameter is defined with all currents going in, I must use a negative sign, and these parameters are A, B, C and D. These are the transmission parameters, okay. The negative sign must get imprinted in your mind. This is the only set of parameters of the 4 Z, Y, H and ABCD that we use a negative sign in front of a negative sign appended to a current or a voltage. It is the current. All right? This is the only set of parameters.
That means that the current direction was taken to be outwards for I2.
That is right. Lord Kelvin said, I will take it out of the
Excuse me,
transmission.
sir.
Yeah.
Sir, one time we cannot use both the voltage generator and the current generator at a point.
Pardon me?
Sir, at one time we cannot use both the current generator and voltage generator. So
No, we don't.
So if we are taking V1 and I2.
It's just the variables. It's not a way of measuring. As you will see, measurement requires only one generator. It doesn't require 2. It's only a way of looking at. You see, I said
These are
out of 4 parameters, V1, V2, I1, I2, I can take any 2 as dependent, the other 2 as independent. I will not be able to connect a voltage generator and a current generator in parallel. No.
Sir, but independent parameters are the forcing parameters.
Right.
Parameters.
Right.
So we want to force some voltage or some current.
Okay.
If we say that V1 and I2 are independent variables.
As I said, this is only a semantics, this independent and dependent. Since I write V1 in terms of V2 and minus I2, I say V2 and minus I2 are my independent parameters. It does not mean that measurements will also be made with one current generator and one voltage generator. You see, even in Z parameters, Y parameters, H parameters, there is only one generator at a time. If you have noticed, all the measurements are made with only one generator, not 2. Okay. So, this independence in the context of ABCD in particular means that 2 parameters V1, I1 are expressed in terms of V2 and minus I. That's all. Okay. No other significance. We will see how to measure them. If you write in full, then V1 is equal to AV2 minus BI2, note the negative sign, and I1 is equal to CV2 minus DI2, and therefore we will see why they are called transmission parameters. Therefore, you see A is equal to V1 by V2 with I2 equal to 0. Now, what does this mean? Let us draw the 2 port. I2 equal to 0 means port 2 is opened, and therefore, the measurement is of V2 with a V1 here, all right, which means that here V1 is the independent supply, generator is V1 not V2. Okay. So, in terms of measurements, measurements have nothing to do with what we call independent parameters, independent currents or voltages. But you see that A is obviously the reciprocal. You see here the transfer function, open circuit voltage transfer function is V2 by V1, and A is the reciprocal of 1 by an open circuit voltage transfer function, reciprocal of a voltage transfer function. Okay. Okay.
So you should have taken V1 as the voltage generator and measured at other end.
That's what I have done. V1 is the voltage generator and V2 is the I am constrained by this.
So V2 as the voltage generator.
I cannot, because I2 is 0. If I connect a voltage generator here, it will definitely send a current. Isn't that right? And therefore, I am constrained by the definition to use a figure like this. Okay? You must remember this essential important points, and you cannot make a mistake, because if you go back to the roots, if you go back to the definition, you cannot make a mistake. I2 equal to 0 constrains me not to put a generator here. Okay? So, generator must be here, and this is why it is the reciprocal of an open circuit voltage transfer function. The reciprocal of an open circuit voltage transfer function may not be itself another voltage transfer function. It is the reciprocal. Okay. Similarly, I can, another parameter that I can find out is C, and from this network. C is I1 by V2 with I2 equal to 0. All right, and therefore, once again my response shall be V2. Agreed? Because I2 equal to 0, response shall be V2, but this time the excitation is I1, the current. Okay. So, what we will do is we will connect a current generator here, or does not matter, we can also connect a voltage generator, that is not a problem. What you have to find out is I1. I have to find out I1 and V2 and this ratio, and you see this is the reciprocal of reciprocal of a transfer impedance. You see, V2 is the response, I1 is the excitation. So, 1 by a transfer impedance, okay, C equal to 1 by a transfer impedance. Yes. All right. Next, let us look at the interpretation of B and D. V1 is equal to A V2 minus B I2, I1 equal to C V2 minus D I2, and therefore B is equal to V1 by I2 minus I2. B is equal to V1 by minus I2 under the condition V2 equal to 0, and D is equal to I1 by minus I1 by I2 under the condition V2 equal to 0. So, let us make V2 equal to 0. Obviously, I cannot connect a generator here. The generator has to be connected here. It is either a voltage generator or a current generator. Whatever be it, the voltage here is V1 and the current here is I1. And what is measured, V2 is 0, and therefore, all that can be measured is I2, the current. Now, if you take the ratio of this voltage to the negative of this current, which means you will get B. So, what is B? B is the reciprocal of transfer admittance. Transfer admittance. Well, negative or positive we will see, it is minus I2. We will see if it comes negative, we will take its negative. Okay. But the dimensionally it is 1 by a transfer admittance, and capital D, as you see, is the reciprocal of current transfer function, 1 by current transfer function, short circuit, all right. But there is something common between all these parameters A, B, C, D. They are all transfer parameters. None of them are driving point parameters. One is a voltage transfer function, reciprocal of a voltage transfer function, reciprocal of a current transfer function, reciprocal of a transfer impedance, reciprocal of a transfer admittance. The word transfer is common to all of them. In other words, the excitation and the response are at different ports, and since every parameter has a transfer associated with it, they should be called either transfer parameters or, a better language, transmission parameters. Okay, this is the reason. Yes.
So while calculating B, we short circuit the second port,
yes,
and apply a voltage source on the first port.
Correct.
Can we do apply a current source at the second port?
No, the constraint is that I have to make V2 equal to 0. If I apply a current source here, I cannot guarantee that V2 equal to 0. Agree? Any other question? Okay. Now, without without much of a discussion now, let us see if we can relate these parameters to the familiar ones, the Z and Y parameters, for example. Okay. Suppose I consider A, the A parameter. A parameter by definition is, if I remember, V1 by V2 under the condition I2 equal to 0. Okay. Let us take the network. I have I2 equal to 0, so the response must be here, and this is V1. I have to find out the ratio of V2 by V1 and take the reciprocal. Now, if you recall, please do follow me. If you recall, our Z parameter definition is V1 equal to I1 Z11 plus I2 Z12. I2 is 0. So, let me not write that. Okay. The other is V2 equal to I1 Z21. Agreed? Therefore, my capital A shall be simply equal to Z11 by Z21. Is that clear? So, if you know the Z parameters, I know the capital A parameter, the transmission parameter. Transmission parameter is simply the ratio of Z11 and to Z21. The other parameter that we can find out from here is the C parameter. C is I1 by V2, if I am not mistaken, with I2 equal to 0. So, I1 is this current and V2. Can you tell me what? Pardon me? 1 by Z21. That is correct. 1 by Z21. Now, I could relate this, I could relate A and C to Z11, Z21 because, very easily, because I kept this open, and you see open circuit, the Z parameters are measured under open circuit conditions. On the other hand, the other two parameters are most easily related to the short circuit parameters, namely Y parameters. For example, the parameter B, as I have said, is V1 divided by minus I2 under the condition V2 equal to 0, and the parameter D is minus I1 by I2 under the condition V2 equal to 0. So, let us take this network. V2 equal to 0 is this, the only thing you can measure is I2, and here you connect either a voltage source or a current source, but the net result is that the voltages and currents are V1 and I1. And now what I have to do is find V1 by I2, V1 by minus I2 or I1 by minus I2. Now, if I write the short circuit parameters, V1, I am sorry, short circuit parameters, I1 is V1 Y11, V2 is 0, and I2 is equal to V1 Y21 because I2 is 0. I am sorry, V2 is 0. The second term I need not write. Isn't it obvious that V1 by minus I2, that means B V1 by minus I2 would be minus 1 by y21 minus.
But the current.
You see, this is the relation for this situation. Okay, I2 equal to V1 y21. So, V1 by minus I2 will be minus y21. Do not forget this negative sign, it is extremely important. It will make a mess if this is not included. And as far as D is concerned, for D you simply have to take the ratio of the two with a negative sign. So, D would be minus y11 divided by, not quite, not quite. Oh, I am sorry, okay, this is perfectly alright because the negative sign is there, okay, minus y11 by y21. Is that clear? This is an example to show that all these parameters, whether H parameter also we related to Z parameters, didn't we? We didn't relate H21 and H12, we will do that in a short while, but any set of parameters can be converted to any other set of parameters. What is the reason? Why can we do it? What is it that facilitates this conversion? Because it is a set of linear equations, two linear equations can be manipulated in any manner you like, all right, without any problem. Okay. Let's take let's take now another important derivation, that is, what is the reciprocity condition in terms of ABCD parameters? Reciprocity condition in terms of ABCD parameters, and for this we appeal to the network itself. That is, what we do is we excite the network by a current and measure the voltage, open circuit voltage V2. Agreed? Now, reciprocity demands that if the current source is taken to the right hand side and the voltage is measured under open circuit condition on the left hand side, the ratio should be equal. In other words, if I change my excitation and response as I2 and V1, under these two conditions, the relation between V2 and I1 should be equal to V1 by I2, all right. V2 by I1 is measured from here and V1 by I2 from here. Okay. This is the reciprocity condition, this is the reciprocity theorem. Now, if I appeal to my equations, you see V1 equal to A V2 minus B I2 and I1 is C V2 minus D I2, then you see under the condition that I2 is 0, okay, for this I2 is 0, what is V2 by I1? It is simply yes 1 by C, okay. And for the other condition, that is I1 equal to 0, you have to put this equal to 0. Let me indicate to you how it is done. I will skip the algebra. What we will do is, for finding out this V1 by I2, we have to put I1 equal to 0. So, if I put I1 equal to 0, I get a relation between V2 and I2, all right. Then in the first equation, you have to find out V1. So, replace V2 in terms of its value I2, in terms of I2, then you can find out V1 by I2. Pardon me? Say it again.
AD minus BC by C.
AD minus BC by C. So, these two should be equal, which means that AD minus BC should be equal to 1 for if the network is to be reciprocal. We have proved it, okay. How did we prove it? We applied the theorem itself, we went to the roots, but if you look at it carefully, these roots mean nothing but equating Z12 to Z21. What is this parameter? V2 by I1 with I2 equal to 0. Obviously, it is Z No, not 1 2.
Z2 1.
2 1, and this is Z12, V1 by I2 under the condition I1 equal to 0 is Z12. So, what we have done is we have taken the condition Z12 equal to Z21 and then applied the definition of A, B, C, D parameters. This is the condition for reciprocity. To summarize, our condition for reciprocity is Z12 equal to Z21, Y12 equal to Y21, this is fine. H12 is minus H21, that is a negative sign, and in terms of transmission parameters it is AD minus BC equal to 1. You see that this is the only set of parameters in which all the 4 parameters are involved. That is, the left hand side is nothing but the determinant of this matrix, whereas the other 3 relate to the off diagonal parameters. Diagonal parameters are Z11, Z22, off diagonal are Z12 and Z21. This is also off diagonal parameter, this is also off diagonal parameters. Only 2 of the 4 parameters are involved in reciprocity if you describe the network in terms of Z, Y or H. But if you take transmission parameters, then all the 4 are involved and it is the determinant of the transmission matrix. This is called transmission matrix. This is what we will start from in the next lecture.